keep quiet? Excuse me? Excuse me, gentlemen? If you could please keep quiet. Could you please keep quiet? Thank you when I'm speaking. All right, let's quickly finish off question 26. 26D we didn't get to. Looks like that, okay? And we're going to do it by looking at the projections of the space curve onto the 3 coordinate planes. So onto the xy plane, we've got x equals t and y equals t squared, if you could please keep quiet. And that makes y equals x squared. That's the relationship. The relationship between x and y is that y is x squared. Because y is t squared and x is t. So y is x squared. Okay, so if we draw that, that looks like your typical parabola. Okay, the xz plane, we've got x is t and y is, sorry, not y, z. Z is t cubed, so z is x cubed. Okay, I am going to draw the axes rather funnily here. I'm going to draw the x increasing in that direction. My cubic goes like that. Now the reason why I'm doing that is in a typical, the convention used in this course for a 3D set of coordinates, once again I wrote y instead of z, is our convention in this course is that the x-axis is coming towards us. So if I want to take some image that's on the xz plane and draw it as an xz plane, and then I want to mentally transfer that image onto a 3D picture, it's easier if I have the x-axis increasing to the left, because then it's a simple sort of pick up and twist to fit it on. Whereas if the x-axis were increasing in the customary direction to the right, in order to take that image and superimpose it onto the 3D picture, I would have to do a full flip around, if that makes any sense. So if I am drawing a picture, a 2-dimensional xz coordinate plane picture that I am hoping to kind of pick up and put onto a 3D system, I personally usually draw my x-axis increasing to the left. That is not something you have to do, but it's something I choose to do. Okay, let me take that away. The yz plane, y is t squared and z is t cubed. So y is equal to z to the power what? T squared, t 1/3. 2 over 3, is that right? Or is it 3 over 2? I'm confusing myself now. What is t? T is z to the 1/3, and I'm putting it in there, so z. No, I think that's right. There we go. All right, and then if you draw that picture, takes a little bit of thinking, but eventually you'll figure out that it looks like this. Whoops, a daisy. Not quite like that. Like that. Okay, that's not immediately obvious. You have to do a little bit of thinking about that, but that is what it looks like. It has a kink in it. Okay, so now the question is, what does our actual curve look like? What does our actual curve look like, given that those are its 3 projections onto the 3 coordinate planes? Question. I flipped directions of the x-axis. Yeah, the y. No, I have not. That is the way it's supposed to be. Y is a function of z, not z is a function of y. It's a sideways graph, if you will, because y is, I've expressed y as the dependent variable. Okay, trust me, that is correct. Okay, so what does this curve look like? Well, before I draw it on the screen, let me draw it in the air. Okay, so here we go. Here's our classroom set of axes. There's my x-axis. There's my y-axis, and here's my z-axis. Whatever my curve looks like, it's casting a projection. I think of it almost as a shadow. It's casting a shadow that looks like a parabola down on the xy plane. It's casting a shadow that looks like the cubic on the xz plane. And it's casting this rather strange pointy shadow on the yz plane. Question?
Could you have made
could have, but then we would have run into the same problem that we did yesterday with a bit of a sign issue. We would have, because the way that the parameters are, so the question for the sake of the audio is, couldn't we have made Z the subject? And we could have, but then we would have chopped out half of the graph. Because given that t is an element of R, t can be positive or negative. But because y is t squared, y will always be positive, and z is t cubed, it means z has the potential to be negative. If we'd made z the subject, we would have ended up stuck in a situation where y and z would both have to have been positive, and in effect we would only have been looking at the first quadrant, if you will, part of that graph. We would only have been looking at the top curve of that graph. By making y the subject, we open up the possibility for z to be negative. There's no, in that equation there's no reason why z can't be negative. Plug in a negative z, you're going to square it and then cube root it. There's no reason for z to be positive. If you'd had it the other way around, with z equals y to the 3 over 2, you would have ended up with a situation where y and z were both positive. So a very similar situation to what we had yesterday. I'm glad you asked that question. I'm sure many people were wondering it. Because we usually used to the vertical axis being the subject of the equation, the variable. Okay, all right. So we've got this space curve that's casting these three very odd shadows. So I'm going to tell you what this curve looks like. This is the twisted cubic that I referred to before. So I find it useful if you first of all think of just the cubic. Okay, so think of the cubic on the xz plane. And think of it kind of being made out of wire. It's like a piece of wire in the shape of a cubic. And what you're going to do is you're going to keep the origin exactly where it is, but you're going to take this wire and you're going to bend it now. So what you're going to do is with the part that's here in the positive, the x positive, z positive quadrant, this bit here, you're going to put your hands in it and you're going to bend it out over the first quadrant, into the first octant. And you're going to bend it in such a way that if you look at it from the top, it looks like a piece of parabola. But if you look at it from this way, it still looks like the original cubic. So you're going to take this cubic, you're going to bend it out so that it's no longer flat against the xz plane. It's now arcing out into the first octant. And you're going to do the same with the bottom leg of this cubic, but you're going to push it out into this quadrant that's down here below the table and behind the table. So you're going to take that piece of the cubic and you're going to bend it out so that it becomes curvy. It's no longer flat against the xz plane. It's curving out into space so that if you look at it from the top, with any but lack any kind of depth perception, so all you're seeing is its xy profile, you're going to see that parabolic shape. But if you look this way, you're still going to, with again only looking at the xz profile, you'll still see that cubic. And the fact is that if you look at it from the front, so as to see the yz profile, you'll see it casting that strange pointy shadow. That is a twisted cubic. And I will try to draw it, but it's really quite a hard curve to draw on a flat piece of paper. Okay, if you could please keep quiet. Okay, once again I've drawn my curve with little gaps in it just to try and sort of trick the eye to show you where the curve is. Of course, the curve itself has no gaps in it. So this part, let me show the left-hand board some love here. This part of it there, t starts negative because t is an element of r and t always increases. So t starts negative infinity and heads onwards. So it starts in with negative x's and negative z's. Always positive y's. So it starts back here, and your particle comes whooshing up through that octant, passes through the origin, and then does a sharp turn and starts whooshing up through the first octant. In such a way that if you looked at it this way, you'd see a cubic. If you looked at it from the top, you'd see a parabola. And if you look at it this way, you'd see that funny pointy thing. Welcome to the twisted cubic. You can recognize a twisted cubic because one component's always linear, one is quadratic, and one is cubic. And they can be in any order, and they can have coefficients as well, like 2t squared or something. But a linear, a quadratic, and a cubic give you a twisted cubic. Now, question, yeah?
Is there a way that we need to indicate that it starts all three of negative? Or do we just draw like as it starts?
Well, the arrow should hopefully do that, because the arrow shows you kind of where, I mean, it starts at t equals minus infinity, so it doesn't really have a start.
But I mean, but how do we show that it comes from the negative, 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 positive?
Well, negative, positive, negative. Well, if you think that your picture's not good enough, and sure enough, my picture's not brilliant, although I must admit, as the years go by, my twisted cubics get slowly better and better. I'm quite impressed with that one. That's similar to the one I did in the TUT yesterday. Who was I drawing it for in the TUT yesterday? I drew it for somebody in the TUT yesterday, and I was quite chuffed with myself. I'd managed to draw such a good picture. So this bit here is the kind of, negative. So you could do something like that if you were trying to make it clear to somebody watching. I'm not watching, looking at it. Okay, all right. I'm not going to spend tons of time on the twisted cubic. Look, I'd be very surprised if we ever asked you to draw it. I suppose there is the off chance. But it's a convenient function to work with because all of the component functions are polynomials. And polynomials are just so easy to work with. So it's a function that we just stumble across in various arenas all the time just because it's such an easy function to just work with at a calculation level. So I do want you to see what it looks like. I do find it unlikely that we'd ask you to draw it. We'd ask you to draw something that's a little bit easier. Or frankly, if I can be brutally honest, something that all your lecturers feel that they can draw themselves. It's slightly hypocritical for us to ask you something that we've struggled to draw. Because hypocrisy has never stopped a lecturer from asking anything, but still I think that it's unlikely. Okie dokie. Let's move on to what the actual title of this lecture is about, which is space curves and intersections. Please keep quiet. Even if you're talking about maths, please keep quiet. There's a hubbub coming from over there. Slightly lesser hubbub coming from over there. Can you please keep quiet? I obviously think I'm talking to somebody else, but actually I'm talking to them. Thank you very much. All right, space curves and intersections. All right, we're going to be dealing with that quite a lot. I'm going to start off with a fairly simple case and then move on to the more complicated case. The simple case is curves intersecting with surfaces. The more complicated case is surfaces intersecting with one another to create curves of intersection. Okay, so let's start with curves intersecting with surfaces. This is really easy and you've already done it. You've done lines intersecting with planes. Now, when you have, so a point in space has 3 coordinates. And when you're trying to solve for a point in space, in a sense, you're trying to solve for 3 unknowns because you're trying to solve for its x, y, and z components. But when that point forms part of a parametric something, like a parametrically described curve, every point on a parametrically described curve is described uniquely by a single value of the parameter. So even though, in a sense, you're solving for 3 unknowns, those 3 unknowns are bound together by a single unknown, which is the parameter value at that point. So when you're trying to find where a curve intersects a surface, what you're really trying to find is what parameter value defines that intersection point, because then that'll give you your actual point. So the process, the technique is to find the parameter value on the curve for the intersection point. And what is an intersection point? An intersection point is the point that exists on the one object and the point that also exists on the other object. In other words, a point whose coordinates satisfy the equation of the one object and the equation of the other object. So algebraically what you do is you combine the expressions of those two objects, in this case a curve and a surface. Best described with an example. So I'm going to do number 28. Number 28a. It says determine where the curve intersects the surface in the cases below. The first one, the curve is a line, a good familiar line from first year maths. And the surface is a plane, also nice and familiar from first year maths. Okay, so you take your parametric equations of your curve and you substitute them into your plane equation. Because what you're doing there is you're telling the algebra, I want to solve for the point that satisfies both equations. And I do that by actually blending the two equations and trying to solve. Okay, so 6, what will that be? It'll be 2, just 2, plus 3, and the y is 3 plus 2 lambda. And the z is minus 2 lambda. And then you solve for lambda. And what you're solving for is the parameter value that will spit out a point that satisfies both of the object's equations. The objects in this case being a line and a plane. Okay, so 12 plus 9 plus 6 lambda plus 8 plus 8 lambda. Oh gosh, now we're doing high school math. 6, 8, that's 14. 12 plus 9 plus 8, what's that? 12 plus 9 is 21, plus 8 is 29, so it's minus 12, minus 29, minus 41. I think so. And that's our value of lambda, unless I've made some silly mistake, which is always possible. Okay, and then you plug that lambda value back into your line. Sorry about that, I'll fix that. And you do a little bit of calculation and you end up with, I'm just going to read it off my notes here, 2 minus 20 over 7 and 27 over 7. And if you look at that and you think, oh my goodness, my heart just stood still, those are fractions, I hate fractions, I'm going to die, this is the worst day ever, then you are not well prepared for your tests and exams in this course. Because you will not be allowed calculators and it's highly likely you will encounter fractions. So go and borrow your little brother's primary school textbook and relearn how to add and subtract and multiply fractions, which you've forgotten how to do since they started letting you use calculators at school. Admit it, you've forgotten how to do arithmetic with fractions. Yeah, okay, there's some honesty there, thank you, I appreciate honesty, but you're going to have to go back to those halcyon days of your adding and subtracting and multiplying fractions. Okay, easy peasy, right? Yes, it is. Let's do B. It's just as easy, but it's just using surfaces and curves that you didn't use in first year. So let's have a look. The curve is, ooh, look at that. It's a twisted cubic. And the surface is z equals 2x squared plus y squared. What kind of a surface is that? What kind of a surface is that? It's got an adjective and it's got a noun. And the noun is paraboloid, and the adjective is elliptical, but thanks for speaking out with confidence. Why is it elliptical? Because one's got a 2 and the other's got a 1. If the coefficients were the same, a 2 and a 2, or a 1 and a 1, or a 10 and a 10, or a pi and a pi, it would be circular. But because they're different, it's a 2x squared and a 1y squared, that makes it elliptical. But the fact that it's z to the power 1 equals something to do with x squared plus something to do with y squared, that is paraboloid. So it's an elliptical paraboloid. Oh my goodness, people are yawning. You won't possibly yawn. Elliptical paraboloids, good grief. It's exciting stuff. I'm at the end of a page, so I'm actually going to jump to the next page for the calculation. Elliptical paraboloid, just we put it there for fun, paraboloid, and that of course is a twisted cubic. Okay, so the way the journal that I'm using works, when I jump to the next page, it does a full jump, and then everybody gasps because the work has suddenly disappeared, but then I scroll back and everything comes back to normal. So just prepare yourself. So z is 3t cubed, x is t, y is t squared, and then I'm still squaring it, so what have I got here? I've got 3t cubed equals 2t squared plus t to the 4. And I'm going to do a page jump. Everybody keep calm. Gasp, thank you. That was well well prepared for. Okay, so let's just carry on. What am I going to do? I'm going to bring everything over to one side of the equal sign and take out a t squared as a common factor. If your instinct said divide through by t squared, then give your instincts a smack, because by dividing through by something, you are immediately eliminating the possibility that that thing can be 0, and you're losing one possible solution. Okay? Or try to avoid dividing through by something unless you are completely positive that that thing is never 0. If it could be 0, rather take it out as a common factor. There's more yawns. Jeez, what's up with you lot? I think I got that right. Those are positive. That one's negative. Yes. T squared is a common factor. Okay, and then I'm wanting factors of 2 that add to give me 3. Plus, so they're both minus. Now I stop and I check myself. That's correct. I've been factorizing quadratics for let's do a sum here. When did I first learn how to factorize quadratics? I was going to say for twice as long as you've been alive, but actually it's about 1.5 times as long as you've been alive. And when I factorize a quadratic, I stop and I check. Okay? Stopping and checking your work is not something that dummies do. It's not something that novices do. It's not something that weaklings do. It's something that people who are good at maths and who are sensible, intelligent people do. Okay. Sensible and intelligent. I'm not that sensible. I'm moderately intelligent. But I've been doing maths for a long time. Check yourself. T equals 0. T equals 2. T equals 1. In other words, there are 3 places where the twisted cubic cuts the, what was it, paraboloid. Let's solve for those points. So now you take those t values and you plug them back into r of t. Let's have a look. There'll be 0, 0, 0. What's t equals 1 is the next smallest, 1, 3, and then t equals 2 would be 2, 4, 2 cubed is 8 times 3, 24. There we go. Easy, right? Okay, how about you give it a go with number 29? Now, if you look at 29, there's a whole bunch there. You're not going to have time to do all of them. So why don't you just pick 1 or 2 and do the others for homework? But you give number 29 a try. Let me just look through my solutions here, see if there are any that in 29 that are particularly fun. Do I mean 29? I do mean 29. Yeah, question?
Where did you get the 3t cubed?
From the question, from the wording of the question. Okay, we're now moving on to something that's incredibly important, and that is the intersection of surfaces. Something that we're going to be doing a lot in this course is doing surface integrals and triple integrals over objects in space, either pieces of surface or solids, where you need to know where the edges of those objects are. You need to know where the edges are, and the edges are almost always, not always, but almost always defined by the intersection of surfaces. So we'll say things like, let S be the piece of the hemisphere such and such that is bounded by the cone, and then you'll be given the equation of a cone. So then you need to know, okay, we've got a hemisphere, but we're only interested in the piece that's actually bounded by the cone, so what piece is that? Where do the cone and the hemisphere intersect? Things like that. Let S, it's frequently S for surface, let S be that portion of the plane such and such that is contained within the sphere, whatever. Then you need to find out which piece of plane is contained within a sphere. So you need to know how to describe where surfaces intersect one another. It's very, very important. So let me basically write what I've just said. Surfaces intersecting with one another. Okay. This process is process, it's not really a process, but anyway, I've written it, is encountered frequently in multivariable calculus, to define boundaries of surfaces or solids. And it's those boundaries that are A, going to enable you to draw the shape, and B, are going to ultimately give you your limits of integration. Okay, your limits of integration are going to be the boundaries of your shapes, and frequently you get those boundaries by calculating the intersection of surfaces. So it's extremely important in this course. Did I put sorry, I just want to look back at my formatting. Did I underline just now when I did surfaces intersecting with curves? No, I didn't, but I'm going to. There we go. Curves intersecting with surfaces. Underlined is now a heading. Bounce back to where I was. Bounce, bounce. There we go. Surfaces intersecting with one another. Okay, cool. Yeah, now, so what do? So you get given a problem and it says, here's a paraboloid, here's a sphere, find where they intersect. So what do you do? It varies depending on the actual structure of the expressions describing those objects. You basically want to combine the expressions in some way by eliminating variables. So you want to kind of eliminate variables and combine the expressions, because once again, what is an intersection? An intersection is the points, in this case it'll be points plural, it'll be the set of points that are common to both objects. If you have a paraboloid and a sphere intersecting with one another, then where they intersect, those are points that are on the paraboloid, but they're also on the sphere. So the coordinates of those points satisfy the equations or the expressions of both of those geometric objects. So what you want to do is you want to combine those expressions. You do that by eliminating variables. And how you do that depends on the example that's in front of you. So giving you some sort of technique can only really be done in a vague sense. So basic technique. Combine expressions by eliminating variables. And it's best demonstrated with an example, and I'm going to do number 32. Here we go. Okay, find parametric expressions for the curve of intersection of the surfaces z equals x squared plus y squared, a nice, neat and tidy circular paraboloid, and x plus z equals 2, that's a plane. Already, well, certainly after a bit of practice, you'd know what sort of curve you're expecting. But you haven't had that practice, so you might not have that sort of gut feel. Picture a paraboloid, like a bowl. It's like a bowl with a rounded bottom that just goes on up forever. And we're going to come along and we're going to slice it obliquely with a plane. What do you expect your curve to look like? An ellipse. An ellipse kind of lying skew in space, or to be a little bit more technical, lying on the plane. So it'll be an ellipse lying on that plane. Okay, so we can already, with a little bit of forethought, know what we expect our curve of intersection to look like, and if it looks different to what we're expecting, we should stop and think. Perhaps our expectations were not so accurate, but perhaps we've made a mistake. Okay, so what are we going to do? We're going to eliminate variables. I've got z equals, whoops, I never put that back, I apologize. I've got z equals x squared plus y squared for the one, and I can write the other one as z equals 2 minus x. So I'm going to eliminate z, and I'm going to say x squared plus y squared equals 2 minus x. Okay, I'm going to bring the x across. And I'm going to complete the square. Squared is plus x, and it would give me a plus a quarter. So I'll put the plus a quarter on this side. There we go. Okay. Now if I stopped there and said, voila, I have my curve of intersection, I would be wrong. Why would I be wrong? I don't have a? No.
I think it's that this is going to be on the plane that we have. It'll be the shape on the plane instead of the shape in the right coordinate system.
Okay, sure. This is giving the shape of the curve. We're only really interested in the curve, the shape of the curve on the plane. What I was hoping was an instinct would sweep across the class to say that can't possibly be a curve because you cannot describe a space curve with a single Cartesian equation. Remember that? Now you look at that and you think curve. Nope, that's a surface, what I've just written there. Okay, that's not a curve. You cannot describe a space curve with a single Cartesian equation because what that is describing in a sense is an elliptical cylinder. So you could actually think of this elliptical cylinder intersecting with the plane in that same curve that we're looking for. Okay, so where do we go from here? What we do now, so if you cannot describe a space curve with a single Cartesian equation, how do you describe it typically? You describe space curves parametrically. So we parametrize that thing. That's an ellipse. We need to parametrize it. Okay, now there's two ways I could go about this. Okay, the two ways are, I could turn that 2 1/4 into a 1 by dividing throughout by 2 1/4. That would be one way. The other way would be to actually build it in, yes. Yes, and 2 plus a quarter is 2 1/4. Sorry, does mixed fractions bother you? I had a tutor once where mixed fractions really bothered him. Yes, it is 2 plus a quarter, which I write as 2 1/4, which I know is a mixed fraction, but if that bothers you, you can write it as 9/4. Mixed fractions no longer taught at school. I had a tutor who hated mixed fractions. He told me all my answers were wrong when I wrote them in mixed fractions. He was from Germany? A German-speaking country. Let's leave it at that. I'm not sure which country it was. And mixed fractions are just not taught there. So I understand there's a bit of a sensitivity with mixed fractions. Okay, all right, but that was a digression. Let us parametrize this thing. Now we know that cos squared theta plus sine squared theta equals 1, right? Sorry, 9/4. Okay, everybody with me so far? All right. Everybody happy? Yes, of course you are. So x plus a half is 3/2 cos squared. Sorry, not cos squared, just cos t. There you go. I've got the first two parametric component functions of the space curve. I still need a third. I still need z. Where am I going to get z from? I'm going to get z from my very original expressions. I have two options. I could either take this x and this y and plug them into the z equals x squared plus y squared, or I could take the x and I could just plug it into the z equals 2 minus x. They will give me the same answer. If they don't give me the same answer, I've made a mistake somewhere. Certainly the 2 minus x is the easier one. Two plus a half ta-da, what my space curve r of t is. Okay, so there's lots of causes and sines and fractions and that looks very busy, but if you just back away from it, what was happening? I had one surface equation, I had another surface equation, I eliminated a variable, z in this case, and combined them. So I said z equals the one thing, z equals the other thing, so the one thing and the other thing must be equal, and I eliminated z. And I simplified a little bit and I ended up with an expression. And I kept in mind that okay, so here's another little thing that might interest you. In a sense, this thing over here, if you want to think of it as a curve, that if you want to look at that and see it as an ellipse curve, you can think of it as the xy projection of your curve of intersection. Curve of intersection. That can be very useful. That can actually be very useful when you're drawing up limits of integration. To eliminate a variable, end up with something that looks superficially like a curve, but it's only a curve if you interpret it in 2 dimensions. But that's still valuable information because it'll be the xy or potentially xz or potentially yz projection of your curve of intersection question.
So will that
Sorry.
just be the projection on the plane, which, like, depending on what thing we've gotten rid of? Is that
Yeah. So if you get rid of z, you'll get an xy projection. You get rid of x, you'll get a yz projection, etc. Was there somebody else with a question back there? Yeah?
Why do you use theta and t as the...
Oh, I was just trying to keep this kind of generic. So that theta over there, I was just trying to appeal to your roots because probably back in high school you used theta. So I was just trying to have something that was very, very generic there.
So
But t would be fine. Yeah. I was just trying to go generic there. Yes.
I don't understand what you did from like that black arrow down.
Okay, what I did was I parametrized. So I looked at this thing. Let me choose a completely different color. Oh, I'm choosing red. I've been told by a colorblind friend, never put green and red together. They're not actually contrasting colors if you are colorblind. Here we go. Light blue. Hopefully it's relatively contrasting. I'm seeing this as something squared plus something squared equals constant. And as soon as you see that structure, you go for cos squared plus sine squared equals 1. Only the constant isn't a 1, so you need to sort that out. You either sort it out by putting an appropriate coefficient in front of the cos and the sine, or you sort it out by actually making the constant into a 1 by dividing throughout first. But when you see that something squared plus something squared equals constant, you say, hooray, it's my birthday, someone's giving me a present, cos squared plus sine squared equals 1. That's what I'm going to use as my parametric expressions. Because then, boom, boom, you've got 2 of your variables expressed parametrically, and there's only the third to go. Also, because to begin with, we thought, okay, this is a paraboloid, we're cutting it with a plane, chances are we're going to get an ellipse, we're going to get a loop. Remember what I said early on? I said if you're parametrizing a loop, cos and sine are your go-to parametric expressions. Cos and sine go hand in hand with loops. Okay, we've run out of time. I need to pause and save the thing. If you can come forward and ask questions if you want.